This video will look at reference guide entry number 3 from unit number 7, which is our first algebraic way of solving linear systems, which is a process called substitution. Now in reference guide 2, we looked at a method for solving linear systems by way of graphing, which was really useful in terms of getting our lines on the graph and finding the place where they intersect. But where it became a little bit problematic is what happens if the lines don't intersect perfectly on the grid. So if they don't intersect at coordinates that are nice counting numbers, like 1, 2 or 3, 5, if they don't intersect right on the grid, graphing became a little bit problematic because you were forced to do a little bit of estimating, a little bit of seeing where they ended up crossing over, and just using your best judgment to determine the coordinates of that point. Which, while it's effective in giving a good idea of your solutions for the variables, if that happened in that case, it could complicate things and make them a little bit less exact. And fortunately, substitution will remedy that. Substitution will allow us to use algebra to find our values of our variables. And instead of it being vague, if they're not nice counting numbers, we will have very specific answers for the two variables in our linear system. Okay, so the process for doing this involves 5 steps. The first of which is to take one of your equations, and it does not matter which one, and to rearrange it for whatever variable is easier to solve for. So you can rearrange it so y is isolated or x is isolated, or whatever letters you're using, you can isolate the one that will be easier to isolate. We'll look at examples of that when we start working on some of the 4 problems below. After you've isolated a variable, you're going to plug it into the other equation, the one that you haven't manipulated, for the variable you've solved for. And what that will do is it will eliminate one of your 2 variables. So we start by solving for whatever variable we want, then we're going to substitute that in. And it doesn't matter, as I said, which variable it is, so long as you're plugging it into the right place. That's going to leave you with an expression that has one variable. That variable will show up a couple of times, but you're going to solve using the distributive property. That's going to give you the answer to one of the letters in the problem. Again, you'll see what this looks like when we start to do some questions in a minute or two. Once we have one of the variables, well, the rest is pretty easy. We're going to then sub in the variable that we know. So again, we're doing a second substitution into either equation and solve for the other one. That will give us our x and our y, or whatever our letters will be. We'll have solved for each. And step 5 here may be question specific. You don't always have to do step 5, but sometimes it will ask you to write your values as a pair of coordinates. And if it does that, then you put your x answer first and your y answer second. That won't happen too often, but if the question ever does say to write, if your variables are x and y, and to write your final answer as coordinates, then that's what you would do. Alright, so that's probably a little bit vague in terms of just hearing the steps, so it will make a little bit more sense when we start to do some questions. So let's do that now. So there are 3 practice problems that are exactly the same as the reference guide that was distributed in class, and then I've added a 4th one onto the end. The 4th one deals with fractions, which is its own separate lesson, but I've combined them both into this reference guide entry into this video. Okay, so you'll notice the first 3 are the same as what was handed out in class, and the 4th one I've added on. It's not on the reference guide that was handed out. So you're asked to solve the linear system below. So when you're asked to solve a linear system, it means to find x, to solve for x, and to find y. Again, these variables may be different. So it may be a and b, it may be c and k, it may be z and b. Whatever it happens to be, there will be 2 variables and you're asked to find each of them. So find x and y in this case, because in the linear system that we've been given, the variables are x and y. So this is our linear system right here. We need to find out what x is equal to and what y is equal to. And if we're using substitution, which we are on this reference guide, well, the first thing we need to do is isolate a variable. So if we look at our top equation, we have 3x and 4y. Well, each of those have coefficients. So we can isolate the 3x, we can isolate the x, or we can isolate the y, but we're going to have to do a little bit more work there. Anytime you have an equation which contains a variable that does not have a coefficient, it does not have a number in front of it, that's probably your easiest one to isolate, because all you're going to have to do is move the other variable to the other side, and then away you go. You've isolated, in this case, x. And that's what happens in this step down here. So you can see that when a variable was chosen to be isolated, it was this x, as was circled above. Well, to get x isolated, we have to move our 2y over. So we subtract 2y from both sides, and we come up with this. X is equal to negative 2y plus 2. And that's what the first step in the list of 5 steps above is telling us to do, to isolate one of the variables. We could have isolated y, but we then would have had fractions, and we would have had to deal with coefficients and things like that. So it's just easier to isolate the one that doesn't have a coefficient if it exists. Steps 2 and 3 ask us to plug that value in, or that expression in, we've solved x equals, into the other equation and to solve. So the other equation states 3x plus 4y equals negative 4. That's the one we haven't manipulated. Well, we've said that x is equal to negative 2y plus 2. So where I see an x in that equation, I'm going to replace it with negative 2y plus 2. And you can see that happening down here. The x is not written in that. It's been replaced with negative 2y plus 2. And where that is especially important is now we only have one variable in the equation. We only have a y. We don't have an x anymore. And when we only have one variable in the equation, we can then solve for it. And that's what we're going to do. So as we work our way through this one, we use the distributive property. So 3 multiplied by 2y and 3 multiplied by 2, or negative 2y, gives us this. Negative 6y plus 6, and we're still adding 4y, and it equals negative 4. We combine our y's, and we solve to get y equals 5. And again, this one's done for you, so I'm going through it a little quickly. When we do the next 3 on our own, we'll talk a bit more about each step. But hopefully you can kind of see what's happening here. You isolate a variable, you plug it in, you solve, and you get an answer for that variable. And now we know what y is equal to. We know y is equal to 5, and it's going to be the same for both equations. So you choose either of the original equations, and where you see a y, you plug 5 in. And so down here, we can see that we've chosen the bottom equation, the one that we originally manipulated. And where I see a y in that equation, I've replaced it with 5. So x is equal to 2 times y equals 2. Well, we know y is 5. So x is equal to 2 times 5 equals 2. So x is equal to, or x plus 10 equals 2. We move our 10 over, and we get x equals negative 8. Okay? This question didn't ask us to write coordinates, but if it had, we would have written it as negative 8 comma 5. Okay? And that's the first one. That's just a quick run through of what this process looks like. So we're going to spend a bit more time now doing a couple of these problems completely. So instead of just doing, instead of just running through steps that are already done, we're actually going to answer these ones as a group. So we are asked to solve the linear system below. So that's typically how these questions will be worded. You're just going to solve. You're going to find the values for each variable. We're going to be using substitution, and we're going to be solving 2x minus 4y equals 7, and 4x plus y equals 5. That is our linear system. Well, when we look at our variables, the first thing we should do is look to see if there's a variable that does not have a number in front of it. Well, this y right here does not have a number in front of it. It doesn't have a coefficient. So let's isolate it. And to isolate that y, all we have to do is subtract 4x from both sides. So when we subtract 4x from both sides, it leaves us with y equals negative 4x plus 5. So we have isolated y. That's helpful because now where we see y in the second equation, we can plug in negative 4x plus 5. So the other equation is 2x minus 4 times y. Well, we know y equals negative 4x plus 5. And we know that all of this is equal to 7. So we've kept the rest of the equation exactly as is. I've just replaced y with negative 4x plus 5. The next thing we're going to do is we're going to use the distributive property to solve this. So I won't worry about my 2x for now. Minus 4, negative 4 multiplied by negative 4x is 16x, positive. Negative 4 multiplied by plus 5 is negative 20. And that equals 7. Well, we have x's there. We have 2x and 16x. So let's combine those. That's going to give us 18x minus 20 equals 7. Now we move, as we all know, we move our 20 over. And we're left with 18x equals 27. Well, we need to get rid of our 18, so let's divide both sides by it. And we end up getting x is equal to 3 over 2. And this is an instance where, using the graphing method, we may have been able to guess that it was at 1.5 or that it was at 3 over 2, but it wouldn't have gone perfectly through the grid on x. So we would have had to do a little bit of educated guessing at this point. But the algebra here spits out an answer, and our x is definitively 3 over 2. So now we have a value for x, so we go up to either of the original equations. It does not matter which one we choose, and we're going to plug in 3 over 2 for x. So I'll do the bottom one. So where I see an x, I'm going to sub in 3 over 2 plus y equals 5. So 4 times 3 over 2 is going to be 12 over 2. So we'll do this step by step. 6 plus y equals 5. We're going to subtract our 6. And we end up with y equals negative 1. And those are our answers, or those are our values for the linear system that we've been given. So we say that x is 3 over 2, and that y is equal to negative 1. All right? On the next one, I'll show you kind of a way that you can check to make sure that that's right. But for right now, we'll just focus on the process, and you can see, hopefully, what's happening here. You isolate a variable, you plug it into the equation that you did not manipulate, you solve by combining like terms, and then solving for whatever variable is left. You plug the variable that you find in the first part into the second part, and you solve for your other variable. So let's look at another one. This one's a little more difficult, as we can see, because we don't have a variable that is coefficientless. So we have 5x minus 3y equals 18, and 4x minus 6y equals 18. So everything there has a coefficient in front of it. So it's not as obvious which one we're going to isolate. So when we look at this, we need to figure out which numbers work well together. Well, 3 and 5 don't really work too well together. They'd be okay. But if we were to isolate, let's say, the x and the top equation, well, 5 doesn't divide into 3 and it doesn't divide into 18. So it doesn't really make sense to isolate that x, because 5 doesn't work well with 3 or 18. If we look at the bottom equation, 4 doesn't divide evenly into 6, nor does it divide evenly into 18. So the bottom equation, x also doesn't make sense to isolate. So in both equations, we would try not to isolate x. It's just going to make our lives a little bit harder the further on we get. Now, negative 3 doesn't go well with 5, but it goes well with 18. Negative 6 doesn't really go too well with 4, but it does go well with 18. So it doesn't matter which y you choose to isolate, but y should be the variable that you choose to isolate. So I'm going to isolate y in the bottom equation, just because 4 and 6 we can at least reduce. So we'll deal with smaller numbers in our fraction. So I'm going to start by moving my 4x over. Because we're getting our y by itself. Then, of course, to get y by itself, we're going to divide by negative 6. And we're going to simplify. So y is equal to 2 over 3x minus 3. So we have isolated a variable, and it's a little bit harder than it had been in the past, but we end up getting where it is we need to go. We have y all by itself, which is good. So put a green line around that, because we're going to need a lot of space to do the rest. So now I'm going to take that, and I'm going to put it into the equation I have not manipulated, which is the top equation in this case. So 5x minus 3 Well, instead of writing y, we're saying that y is equal to 2/3 x minus 3. So that's what we're going to plug in there. And then all that is equal to 18. So now we're going to use the distributive property as we did before. So we're going to have 5x. Now we end up with minus 3 multiplied by 2/3 x. Well, that's going to give us minus 6/3, which is minus 2x, negative 2x. The negative 3 multiplied by negative 3 is positive 9. And all that's equal to 18. So in that step, I just used the distributive property and distributed my negative 3 amongst both things in the brackets. Now we're going to combine what we can. Well, we're going to have 3x here. 5 subtract 2 is 3. Both have x's on the end. And then we're going to move our 9 over, which is going to give us 3x equals 9. Divide out our 3. And x is equal to 3. Okay, so hopefully you're starting to see the process that's happening here. We have one of our variables. So now we're going to find the other one. Well, if x is equal to 3, we can go to either equation as we did before and plug x equals 3 in. So let's choose our bottom equation this time. So 4 times 3 minus 6y equals 18. 12 minus 6y equals 18. So again, we said that x is equal to 3, so where I see x in the bottom equation, I have plugged in 3. We'll move our 12 over by subtracting it from both sides. We end up with negative 6y equals 6. We divide out the negative 6. We get y equals negative 1. Okay, so we end up getting two pretty nice numbers, even though we had a fraction for y when it was isolated. It ends up working out okay. Now I mentioned before that I would show how to check with this one. Well, that's what we're saying that the answer is. We're saying that x is 3 and y is negative 1. And we feel pretty confident about that, but it's a test, and this is a question that's worth 3 or 4 points, so we want to be sure. Well, if we want to be sure, we can check our x and y values in both equations. And if it works with both equations, well then we're probably good, or we're almost certainly good. So we're saying x is 3, and we're saying that y is negative 1. And now when we work this out, we should get 18 on both sides. And we can see that we do. So it works with our top equation. Now let's make sure it works with our bottom equation. So where I see an x, I'm going to substitute in a 3. Where I see a y, I'm going to substitute in a negative 1. And we're going to hope that we know what we're doing and that it works out. And it does again. So this check is really, really useful if you have the time to do it, and some questions may ask you for it. But even if they don't, take your value for x, take your value for y, and plug them both back into the original equations, into both. And if it works out, if what you get as your final answer makes logical sense, like 18 equals 18, we know that, and 18 equals 18, if you have the same number on both sides of your equation, then you're good. Then you can be confident that the work you did has given you the right answer. So sample problem number 4 has another complicator. So we're still going to solve this using substitution, but this one looks way worse than the other ones because this one has fractions. Every value is a fraction, in fact. So that doesn't change how we're going to solve it. It just delays how we're going to solve it, because the first thing we need to do is we need to get rid of the fractions. That will make our lives way easier. So let's get rid of these fractions. Well, in order to get rid of the fractions, you look at the denominators that are involved. Well, in the first one, the denominators of each fraction are 10, 2, and 5. and you say, what is the LCM of those values? Just erase this. Well, the LCM, the smallest multiple of 10, 2, and 5, is 10. So the LCM of the top equation is 10. So what we're going to do is we're going to multiply everything by 10. If you're wondering how that's going to help, we'll take a look and we'll see. So I've multiplied both sides by 10. Well, when we take 10 and multiply it by negative 1 over 10, we get negative 10 over 10x. We'll reduce that in a second. We multiply 10 by 1/2, we get 10 over 2y. We'll reduce that in 1 second. We multiply 10 by 4 over 5, we get 40 over 5. And now, if you can kind of see what's happening here, you're going to be able to make all these nice numbers. Negative 1x plus 5y equals 8. Well, that looks like a much easier equation to solve than negative 1 over 10x plus 1/2 y plus 4 over 5. So that was our first one. Let's take a look at our second one. Our numbers are 7, 3, and 21. Well, the LCM for those is 21. So same idea. We're going to take each side of the equation and we're going to multiply it by the LCM. And what will happen by doing that is all of our fractions will be gone. So let's take a look at how that will work. 21 times 1/7 x is 21 over 7x. 21 times 1/3 y is 21 over 3y. And 21 times negative 2 over 21 is negative 42 over 21. Well, now let's reduce. 3x plus 7y equals negative 2. And now we have these two nice equations that we can use in order to solve our linear system. So let's do that now. Well, which is the variable to isolate? It looks like negative 1 is going to be our best variable to isolate. Negative 1x, sorry. We'll isolate x in the blue equation. So in order to do that, we're going to take our 5y and move it over. Just put a line here. So we'll take our 5y and we'll move it over to the other side. So as to get the x on its own side of the equation. Well, we don't want negative x, we want positive x. So we're going to have negative 1x equals negative 5y plus 8. Divide by the negative 1. And when we isolate x, it's equal to plus 5y and negative 8. Now we've isolated x in our blue equation, which means we have to plug it into our red equation. So where I see an x in that equation, I'm going to substitute in 5y minus 8. I'll use the distributive property as we did before, and we'll solve. So 3 times 5y is 15y. 3 times negative 8 is negative 24. We keep the 7y and the negative 2 because we're not ready to deal with them yet. But now we are. Let's combine our y's. So 7 plus 15 is 22, so 22y. And now we'll move our negative 24 over. So 22y minus 24, so we'll add 24 to both sides to do that. And that will go up here. When we combine that, we get 22y equals 22. So we do all this work, and y is equal to 1. So we did all that work just to get y equal to 1, but now that we have that, we can just plug it into either equation. And since I can just see only the red equation right now, let's plug it into that one. So to solve for x, where I see y in this equation, I'm going to plug in 1. It's going to leave us with 3x plus 7 equals negative 2. Subtract 7 from both sides. Negative 2, subtract 7. That leaves us with 3x equals negative 9. When we divide out the 3, we get an answer of x is equal to negative 3. Okay? And if you want to check it, you can plug it back into the fractions if you want, or you can plug it into the equations that I circled in green above. Okay? And that is the process of substitution. It involves being very careful with your algebra. It involves being very careful with how you maneuver each equation and how you isolate variables and how you sub them in and multiply and all of that sort of thing. But the process is repetitive. Once you understand what to do, it doesn't change. So once you understand what to do, every question will look the same, just the numbers and sometimes the letters will look a little bit different.